Okay. So again, we're deciding whether these are true or false statements. Let's see what you guys got for these. Number 1. False. Good. We do not break up an exponent over plus or minus. We have to actually boil that out. A plus B times A plus B. All right, number 2. True. Good. Exponent can be distributed over multiplication division. Number 3. False. What's the issue here? Good. This should be distributed both pieces, of course. Awesome. Number 4. True. Good. All right. Number 13. False. What's the issue here? Yeah, 2 is not included with that exponent of n, so only the x here is the nth power, not the 2. So, alright. Number 14. False. What should it be instead? Good, 1 over x. 15? True. And 16. True. Good. Questions on those so far? Awesome. Alright, let's bring up another chunk. Ooh, yeah, those logs, they come back too. Logs and exponentials, gotta know how to solve logarithmic equations. What is natural log of 1? Zero. Talk to your short partner real quick. What's natural log of 1? And if you forget, draw a quick little graph. Yeah, you need to know your graphs too. Natural log of 1? 0. Good. Natural log of 0 is 4. Or sorry, natural log of 1 is 0. What's natural log of 0? Good. Good. If you think of your graph, you got that as a okay, sorry. Continue on with this. Don't you love being this close? Ah, sorry. Cancel. I apologize. And I chose the one that has so many more to it too. Alright, 1 more minute. 2 more minutes. No more minutes. Alright. 30 seconds. Yes. Okay, number 5, true or false? Let's take a look. Can we factor out an a on the bottom? Why, yes, indeed we can. A over a times b plus c. So now we can reduce those, and that is 1 over b plus c. So that is true. Basically, every single piece. All right, number 6. 7. False, guys. Number 8. Good. What's the issue there? Yeah, D doesn't have an A, so you can't reduce it with all pieces. All right. Logs. Number 17. True. Yeah. So this is a power, and we know that a power raised to power gets multiplied here. 18. True. Do we have a property for that?
Oh, that's one. That's this.
Yeah, this is the property. So when our argument is multiplied, then we can separate as 2 logs being added together. They tricked you. They like kind of put the pieces and made it look similar. So it's our argument being multiplied, the pieces get added together. So if you think back to your exponent rules, we have same base. So bases are multiplied, exponents get added. That's the idea here. Because remember, this represents exponents. So sorry, that was false. Were you good with that one? Okay. Number 19. False. This negative was not included, so this should be negative 16. All right, and then number 20. False. Again, same idea. The negative is not included in the display. Okay? Ooh, more logs coming at you. Alright, we're going to multitask a little bit more. While you're working on this, make sure your name is on your summer assignment. If you have any work that you did off the paper, I'm going to pass around staplers for you to staple that together. And just going to put that as period 2. So make sure your name is on the summer assignment and period 2. And then once you got all together, pass it forward. All right, do we need one more minute? No more minutes? One more minute. Any other summer assignments? All right, let's go ahead and take a look at these. Number 9. Got one false. Two trues. Retaining thing is true. Retaining thing is false. What is that? Yeah. I got you again. Good work, you false people. So our argument has to be divided in order for us to get this. This is actually similar to change base. Okay. So then number 10. True. That's what we just did above, right? So when our argument is multiplied, it's log of each piece added together. When our argument is divided, it's log of the top minus log of the bottom. Number 11. That better be a resounding false. Our natural logs do not simply cancel out, just like sine of 5 over sine of 6 is not 5, 6. These are operators. Log, natural logs are operators, just like addition, square rooting, absolute value mean. So again, square root of 5 over square root of 7, that would not just cancel each other. Okay, number 12. I heard a few truths. True. Yes, good true. We would exponentiate both sides there. So the way to solve this is we would exponentiate both sides. So take each one and put an e in front. And then those simplify and we get e equals. Okay. Out of log length. Number 21. False. Wait, see? False. So remember the same thing as c over 1. So this would be negative a over b times 1 over c. Height 23. So we have, oh goodness, that's confusing. A over b. No, a over b c. Hold on, let me see this. A over b is on top. No, a is on top. So this is a over 1 times the flip that guy. So now that you know that this is the big fraction bar, what do you guys think? Does that make sense what I just did there? Yeah. I'm sorry. With this being the big fraction bar, so the top is a over 1, and then this is our guy that we multiply and flip. So we have h over b, so that would be false. I'm sorry. That was confusing. Okay, questions on those ones that we just went over? I recommend you review your log properties. Very soon. Alright, and then we have just a few more to simplify. That's right, there's more. Alright, those should go a little faster. Alright, what do we get for 24? False. Every time you make this mistake, I lose 5 years off my life. I'm pretty sure I'm going to die like next year based upon that. We cannot break up the square root over plus or minus, similar to our exponents. Number 25? False. 26? False. Only Chuck Norris can divide by 0. You are not Chuck Norris. 27? False. What should 27 say? Alright, go ahead and do these next ones, go. 28? Almost. Gotta get that common denominator. So our denominator would be P, D in the first place. Alright, 29? Multiply straight across. So cross multiplying. I think some of you, I told you we're not allowed to do that. You're allowed to do that. So cross multiplying can only be done when we have a single fraction equal to a single fraction. Let's make it. Looks like this is kind of trying to combine that ish. All right, number 30. False. Ordered operations, and you cannot bring this into the parentheses if it's a All right, 31. False. All right, and finally. Is there anyone that did not get the piece of paper I just handed out? All right, 32. False, good. 33. False. 34. False. What do we need to change here? Yeah, this formula is true when it's a difference of squares, so we've got to have a subtraction sign. All right, 35. What's wrong with 35? Good. The first time I did this, I actually didn't catch that. So difference of cubes, it's not 2AB, it's just AB. Good. Congratulations, you survived some of the algebra reminders. Hopefully this helped you identify if you need to practice some things, and I think a lot of us should look at logarithms. Okay, questions with any of that? Okay. So you have in front of you, yes, sorry. Oh, you're a caddy? Yeah. Okay. How can you keep an eye? Okay. So in front of you should have a purple assignment sheet. Go ahead and take a look at that. We'll bring it over here. This is our tentative pacing for the unit. So you'll notice the first unit of calculus is actually overlaps with pre-calc, and that it's over limits. So whether you had pre-calc or pre-calc honors, everyone has learned limits. Now we do have a little bit of new when we get to differentiability, and which class you had, you may or may not have dealt with that. All right, so today and tomorrow we're going to talk about pretty much everything with limits. So looking at it graphically, algebraically, factoring, multiplying by the conjugate, our trig limits, and limits at infinity, or end behavior for what's happening in hands. So on the third day of class, we get a little short quiz on limits. Woo-hoo! It'll just be a short one, and then we'll talk about continuity and intermediate value here. You've dealt with continuity in Algebra 2 and pre-calc, so we're looking at it from a calculus perspective. And then on the 7th is a prerequisite skills quest. So on Blackboard, you will find some worksheets that are just practicing prerequisite knowledge. So Algebra 2 stuff, pre-calc stuff. This quest is going to be over prerequisite skills. So stuff that was on the summer assignment and pretty much anything you've learned up until this point. So on Blackboard, those worksheets are just there for you, for your practice. Do what you need to prepare for that, to make sure you are stellar with all your previous math knowledge. Because all that's really important to be successful in calculus. So this just kind of bring it all to the forefront of our minds and get ready. right, and then we start to dive into a little bit more of the calculus portion of it. And as of now, our test, I think, is 19. And so something with calculus is that all of our assessments are cumulative. So our Unit 1 exam will include some of that prerequisite knowledge, so this probably comes into play more when we get to later units, but everything's cumulative, so make sure that you're always practicing previous material as well. But this will include some of that prerequisite knowledge. All right, questions with the pacing here? It may change, hopefully we get 12 or 14 snow days. Not yet, you never know. But, so if things change, we'll just say it. All right, a couple of things here at the bottom. So a lot of you have heard of Khan Academy. It's a great resource. Khan Academy has actually paired up with College Board to create videos for AP Calculus. There's also another resource called Getify.com. It's similar to Khan Academy in that it has videos and practice problems. So I recommend checking that out as well. Okay. So let's go and take a look at the package that we're trying to. This is what we're going to be using today and next class. It's both classwork and homework, so I'll tell you which problems to do, but we're actually going to be doing some handwritten notes, so go ahead and get out a blank sheet of paper, but keep that packet nearby because we'll be referring to that as well. We'll be using notebook paper, so if you want to keep an actual math notebook, we'll do a lot of handwritten notes in here. So it's up to you what paper you want to use. That's fine. Yeah. There's not a time in which you have to have graph paper, but we will be sketching graphs, so if you want to have nice grid behind it, yes. But you'll see mine are just round sketches. And remember, guys, if you ever need paper, there's some over in that way. Okay, so I want you to start off by talking to your shoulder partner about limits. What is a limit? What has to be true in order for the limit to exist? What makes this a limit doesn't exist? And just anything you remember about limits from your previous classes. Go. Alright, just bring it back up front. So, who would like to tell me something they remember about limits? Be brave. Stay a while. See you on the next event. Okay. Hold on, you are Lauren.
So if there's like a small plus or minus sign, minus or something like that.
Wonderful. So she's saying if there's a little plus or minus next to the value that x is approaching, then that indicates left or right. Which one's which? Yeah, plus is right, minus is left. Good. What else do you remember about limits?
It has to be the same going to the left and from the right for it to be a limit.
Very good. So we have what's called one-handed limits. So the left-hand limit, right-hand limit, those are one-sided limits. So that's looking at it from just that one direction. Can I still do jokes about one direction? Okay. And so for the overall limit to exist, the limit from both sides has to be the same. Very good. What else do you remember about limits? On that note, do we have to have the point be the same as the limit? No, good. We're only talking about what it's approaching. We don't really care what's actually happening at that value. Anything else? What would be a case in which the limit would not exist? Oh, not approaching, same thing. Good. So what might that look like? Joan, good, good. Joan, Angelina, what did you say? Good. An infinite, so if it's not approaching a single value, so if it's up to top, down to bottom, with those sound effects. Anything else? Yeah, so the vertical asymptote, good. So we often have those infinite limits with asymptotes. There's one other kind of weird type that yeah, the oscillating, yeah, like a guitar string. But it continues. Okay, good. So again, it's trending toward a single value, a single number. Now, something with calculus you'll notice is that we are very picky about notation and very picky that everything is mathematically sound. So in calculus, we say limits do not exist. A single point, like a point of graph, is undefined. Okay, so that is actually very important. If you said that a limit is undefined, that would be wrong. Okay. All right. So limits. So let's talk about what the definition of limit is. So we said basically three things have to happen to get the definition of a limit. We discussed that basically it's trending toward a single value, but essentially three things have to happen. Our left-hand limit, so as x approaches a from the left of a function, let's just say it equals L. So our left-hand limit has to exist. Our right-hand limit has to exist. And they must equal each other. So the limit as x approaches a from the left must equal the limit as x approaches a from the right. Okay, so really the left-handed limit exists. The right-hand limit exists. They're equal. So in order for the overall limit to exist, those pieces must be true. Okay, so in this event, we would say the limit as x approaches a of f of x equals none. All right, and again, we're just going to make a little note here that f of a does not have to exist. Does not have to be defined. So again, that point doesn't have to be there in order for the limit to exist. It's great if it is, but it's not. All right, does that all sound familiar? Hopefully that was only a few months ago, not a full year ago. Okay, and so we talked about some types in which it would not exist. Let's draw a few examples of that. Limit does not exist. And it is okay to write D and E for this. In calculus, abbreviations are a big no-no except for a handful of them. D and E is acceptable. You can write D and E instead of does not exist. But you cannot abbreviate like min, max, increase, and decrease. I know, they're picky. It's really annoying when I have to write out a picture. Alright, so limit does not exist. We talked about if it might be a jump. So this could be an example in which the limit would not exist. Okay. We talked about how there could be a vertical asymptote. And they don't have to be going in different directions. They could be going in the same direction. And we talked about oscillating. Ooh, let's bring some trig back into it. Do you guys remember how to do your sine graph? Quick, sketch a little sine graph. What is sine of 0? That's a good start to it. Alright. So these are just some examples of which our limit would not exist. We don't always have graphs. Sometimes graphs are given to us. Sometimes we look at it just how it's written. So I'm just going to call this jump. Asymptote. And oscillate. Now, sometimes we're presented with limits on a graph, sometimes numerically, like in a table. And with the table, we're just looking to see what it's trending toward, what the numbers are going for. But let's go ahead and take a look at your pack that you have here. That first page. And I want you to go ahead and let's just go with this guy here. Let's take a look at this one. So it says, describe the domain and then find the limits. All right, so for this one here, what is our domain? Go to speed for this one. Good. Negative infinity to 1. And union 1. All right, so we already see there could be a potential issue for a limit, perhaps, because it's not defined there. But we'll see if it causes ground source. So this one, we're saying the limit as x approaches 1 from the left of f of x. What is going to be my limit as we're approaching? So here's 1. As we're coming from the left, what is that value approaching? 2. Good. So again, we're saying as x is going toward 1 from the left, my y value is approaching 1. So now let's take a look at it from the other side. As x approaches 1 from the right, my y value is approaching. Oh, that's looking good. So my overall limit then is, woohoo! And what is the function value at 1? Undefined. Good. So again, undefined. All right, it's really important that anytime you're working with limits that you have your limit notation. You'll see this more as we're working through algebraically. It may be tedious, but it's just the way life is. You do need to have that limit notation, and you do need to define what function you're taking the limit of. You need to have each of these pieces, the word limit, what the value is approaching in the function there. Okay. I want you to go ahead and do this one. Once you get your answers, check it with your shoulder partner, see if you got the same thing. Double check with your shoulder partner. All right, what's our domain? Infinity to infinity. Good. Even though there is this jump here, every single x value is defined along there. You think that one doesn't exist, but oh wait, it does. Okay, so our domain's infinity to infinity, no breaks in there. Okay, left hand limit, right hand limit, overall limit, good, does not exist, and the function value at 1. Okay. All right, questions on that? Okay, so let's go back to our hand limit. Okay, so we have certain laws, or limit laws, certain properties of our limits. So let's go ahead and recap those. Alright, so suppose the limit as x approaches c of f of x, and the limit as x approaches c of g of x exists. Okay, so notice our limits have to exist in order for these properties to be true. Alright, so then we have the following properties. So we have our constant property. You don't really have to know the names. Alright, so our constant, we have the limit as x approaches c of any constant. So the limit as x approaches any value of our constant is just going to be the constant sum. So for example, the limit as x approaches 2 of 5 is 5. And if we stop and think about this, think of your graph. No matter what value, no matter which x value we're approaching, the y value is going to be the same all the time, right? So it seems pretty obvious. You probably aren't going to get that on the AP exam, but stupid. Alright. Our next one, we have the identity property. approaches c of x is d. So we're just dealing with the function y equals x. And as you know, that graph, whatever your x value is, you have the same y value. So for example, the limit as x approaches 3 of x is 3. If we think of our graph, when x is 3, ideally, our graph y is 3. Again, pretty easy. Questions so far? We good? Does it sound familiar? Look familiar? Bringing back good memories, hopefully. Springtime. Alright, next up we have our coefficient. Alright, so the limit as x approaches c of b times f of x. So basically what this is a coefficient in front of our function. We can take that coefficient and just bring it out in front of our limit. So same thing as our coefficients. Limit as x approaches c. Okay, so again, that coefficient, if it's in front of our entire function, then we can pull that out. So an example of this, the limit as x approaches 4 of, let's just say, 2x. It's the same thing as 2 times the limit as x approaches 4 of x. So again, I can take that coefficient out of front. A lot of these properties seem like common sense, but it's still good for us to know that. All right. Next up, we have our sum and difference. Pretty much, if we have a limit of two functions being added or subtracted, we can break up the limit over those functions. So the limit as x approaches c plus b of f of x plus g of x. Okay, so I've got two functions being added together there. Let's go and say, so it's the same rule for both sum and difference. I'm going to say plus minus. Then I can go ahead and break that up into the limit of the first. Limit is x approaches c of f of x. Plus minus. The limit as x approaches c, g of x. And again, if it's addition, it stays as addition. If it's subtraction, it stays as subtraction. Alright, so an example of this. Limit as x approaches 2 of x squared plus 2x. It's the same thing as the limit as x approaches 2 of x squared plus the limit as x approaches 2 of 2x. Questions with that one? And it's pretty similar for your product and your quotient rule. So let's go and take a look at product. Limit as x approaches c of f of x times g of x. We can break up that limit for that as well. Limit as x approaches c of x. X approaches c of g of x. And this is also true for quotient, but the only thing with quotient is that that bottom function, the limit can't be 0, right? Because we can't divide by 0. So we gotta write out quotient. Limit as x approaches c f of x divided by g of x. The same thing as the limit of the top function. Divided by the limit of the bottom function. disclaimer that the limit as x approaches c g of x not be zero. Okay. Questions with any of those? Now there's still one more property that's pretty important. Does anyone happen to remember what that property is? It's another form of operation. We've done addition, subtraction, multiplication, division. What else could we possibly do? What'd you say? Exponent, good. So we also had the power rule. And this is off the top maybe. Alright, so we also have where's the power? The limit as x approaches c of f of x raised to the power. We can actually take that limit inside of the power outside of it. So we have the limit as x approaches c of f of x. That whole thing raised to the power. Now this also extends to the root rule. If you remember your roots, so like square root, cube root, those can be written as powers, right? So likewise, if I have the limit as x approaches c of the square root of f of x, this can be rewritten as x, or f of x to the 1/2, and that's taken outside. So we could rewrite that as the square root of that. So sometimes, depending on what resource you look at, some people might call it the same thing. Sometimes they write it as a separate one. It's like the root rule if you can't give it a name. But it comes from our power rule because roots can be written as powers. Okay, lots of limit laws there. Questions with any of those? Okay, so let's go ahead and take a look at doing some of these. Pretty much with our limits, the idea is that you're going to try direct substitution first, and then if it doesn't work, we look at other ways to manipulate it algebraically. But let's go ahead and take a look at your first station. Let's see your first station of the inside. Alright, so we can see here with number, we have some of our basic properties here. So the limit as x approaches to 3, what is that going to give me? What's my result going to be? 3, yeah, so be careful. It's whatever you're calling it. And again, it's because we think of that graph. So a lot of times with limits, if you're stuck, think of what the graph looks like. That might be helpful for you. We have just that constant. All right. The limit as x approaches -4 of x. What is that? -4, good. And notice if you think of in terms of direct substitution, I try taking -4 and substituting in, and you get -4. Over here, if I try to take 2 and substitute in, there's nothing substituted. We're still left with it. Good. All right. Letter C. What do you guys think the answer is for this one? The limit as x approaches to of x squared. What do you think the answer is? 4. Now, how did we get 4? What did you guys do? Yeah, direct substitution. We take that 2 and substitute it. Now, technically, what we're able to do here is rewrite this as the limit as x approaches to of x quantities squared, right? And then we use the identity property. Take 2, substitute in. The identity property says, hey, that's 2, 2 squared is 4. But do you have to write out all of those laws every single time? No. Thankfully, no. That would take so much time and effort. So try direct substitution first, but you do not have to write out all the little individual laws. All right, get number 5 and 6. Try substitution. Alright, what do we get for number 5? I heard teen, but I didn't know it was in front of it. 19, good. And number 6? So, once again, what we technically have happening here is this is the limit as x approaches 2. we can break it up over each piece and bring out that coefficient and bring out that power. So I technically have this. Oops. Nice. Plus the limit as x approaches 2 of 3. So technically that we're applying all those limit laws, but again, you do not need to write out the limit laws, just try direct substitution. Now I know some of these we can do in our head, right? We're able to probably do this in our head. This one you might want to write a little bit of work. But I highly recommend that when you're doing limits and you do direct substitution, start out by writing out what you've put in, so write out that setup. So over here I would have actually written, all right, so I've got 1 times 2. So on top I have 2 times 1 is 2 minus 1 over 1 cubed is 1 minus 2, and then simplify it from there. Now notice that once we are actually evaluating the limit, I am no longer writing the limit in front of my answer. Right? I just actually have the answer. What do we say this one was? Negative 1? Negative. I am no longer writing the limit. So once you've actually evaluated it, when you do that direct substitution, don't write limit anymore, because you have taken the limit by doing that, by directly substituting. Okay, I'll leave number 7 for you for later. Questions so far? Okay, so now sometimes we get into the event where when we do direct substitution, we run into issues. So let's go ahead and go back to our handwritten notes. Alright, so let's do the limit as x approaches of x minus 8x plus 12 over x minus 2. A rational function here. So the limit as x approaches 2 is x squared minus 8x plus 12 over x minus 2. When we try to do direct substitution here, let's see, we get 2, and I get 2 squared is 4. 2 times 8 is 16. Is 12. So we get 2 for the bottom, and I get 0. Alright, what do we get on top? Yikes, we get this thing called 0, 0. This is called an indeterminate form. Indeterminate form. Which means we can't determine what the limit is based upon information. So when we get 0 over 0, another form of indeterminate form would be infinity over infinity. But the same as we don't know what's happening, we're not sure what the exact limit is, we have to do something further. One of our techniques is factor. So we look here and we say, all right, can we maybe factor this? Can we reduce this down to something that which we can implement into? So let's go do that. Let's go ahead and factor. Now ideally we can do this factoring pretty quickly. So this limit is equal to the limit as x approaches 2. Notice I have not evaluated it yet, so I'm still writing limit. What does my top factor into? What multiplies to 12 but adds to negative 8? Negative 6, negative 2, right? So we've got x minus 6, x minus 2 over x minus 2. Are we okay with that? Okay. So again, I have not evaluated the limit. I'm not able to do direct substitution. Notice here, I did direct substitution, yield 0, 0. I'm not writing limit. But here I'm manipulating it, so I'm still writing limit. If you do not write the limit, it's wrong, because it's incorrect notation there. You're saying that this limit equals that function, which is not true. Okay, so now I look and see, hey, I can actually redo this. I can reduce this. I can simplify it down. Alright, so this is equal to the limit as x approaches 2 of x minus 6. Now, can we evaluate this limit? Yeah, so much easier. Alright, so we put in 2, 2 minus 6. What do we get for our limit? Negative 4. Okay. Notice I am evaluating it. I put in that number, did that direct substitution. I want me to write it. Now, I do want to make sure we understand that this equation is not the same as this equation. This is a simplified form with a domain restriction. This graph looks just like this graph, except what? What has happened? Oh, good. We have a hole here at x equal to 2. So these are not the same functions. They're very, very, very close. They're not the same functions, but they're very close. So they look the same, except this does not have the hole for this one does. But because the hole doesn't matter for our limit, we're able to simplify that down and say, hey, I know this is going to look like that graph, except at that point, but that's okay. No, just do a direct substitution. All right, questions with that? Okay, let's go and try another one. So the limit as x approaches -1 of x cubed plus 1 over x plus 1. Right, so again, we're always going to try direct substitution first. And please, 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 please try it, because sometimes you'll get a crazy looking problem, you're like, oh, I've got to factor that. But really, you could have just done direct substitution and save yourself a lot of time. Alright, so when we try direct substitution, I take -1, put in, I get -1 plus 1, -1 plus 1, whoops, that's 0 over 0. No good. Alright, so let's try factor. Alright, factor, oh man, sum of cubes. Check with your shoulder partner, how do we factor x cubed plus 1? Oh, just over size here. You factor it, I'm going to factor up here, let's see if we get the same thing. It's been a little while for all of us. You guys agree with that? I got 2 head nods, and then else. I apologize. I should be having an equal sign here. Make sure that I'm saying this limit equals that limit. All right, continue on. I want you to finish out the limit and see if you get the same thing. Make sure you're using proper notation. Anytime you write a new step and we're still haven't taken the limit, you have to write that limit notation. Very, very important. And again, once you get your chance, you're going to check with your shoulder partner. Great question. So what's your answer? So it's when you have 0 over 0 that we have here. Oh, yes, okay. Okay. To 11. Okay, so say if you can remember. Alright, we reduce these. Limit as x approaches -1 of x squared minus x plus 1. And what do we get when we substitute that in?
3.
3. Alright, questions so far? Okay. Actually asked a wonderful question. He said, okay, well, what if when we do direct substitution, instead of getting 0 over 0, we got 0 over some number? It's a wonderful question. What is 0 over any number? 0. So your answer is actually just going to be 0. So it is okay to have an answer of 0. But when we have that 0 over 0, since we cannot subtract 0, that does not yield enough information for us to make this one. Let me ask you another question. This is going to come into play later, but what if I had number, oops, let's put that at the eraser spot. What if I had number over 0? That's undefined. What does that indicate when we have that? Good. What's happening on the graph? Yeah, it's a vertical asymptote. So what we have happening for that some type of bird class that is going on. Okay, so that's going to come into play in just a moment. All right. Good. Wait a second. Alright, let's just see if you remember what to do with this. If we don't get to it through it all, that's fine. We'll pick up with it next time. But let's take a look at this example. The limit as x approaches 4 of the square root of x minus 2 over x minus 2. Limit as x approaches 4. The square root of x minus 2 over x minus 4. Again, make sure you always try direct substitution first. So get square root of 4 is 2 minus 2. 4 minus 4. Oh no, we get 0 to 0. Alright, do you guys remember what we do with these ones? We can't factor that. Yeah, we want to multiply by that quantity. Now, again, your mathematical notation needs to be proper, so you can't just start saying, all right, equals square root of x minus 2 times square root of x plus 2. No. This limit does not equal the function, okay? Again, it's very important that you rewrite limit in front. Or, I'm okay with you saying off to the side, all right, this is my graph. I don't want to write limit a million times. Here's my work. So let's do that. Square root of x minus 2. Over x minus 4. And I want to multiply that. Make sure you put that in parentheses. Square root of x plus 2 over square root of x plus 2. Make sure you're still using proper mathematical notation. This is equal to what we're about to do. What do we do with these on top? Yeah, we've got to FOIL it out. Alright, so we would get x, those cancel, minus 4 on top. Now on the bottom, we don't actually want to FOIL those out. That would make it worse than what we have. We want to leave that in factored form. And then now what's going to happen? What wonderful, beautiful thing occurs? Yeah, these reduce. So then I can come back over here and say this equals the limit as x approaches 4 of 1 over root x plus 2. Okay? Now, if you do this, I will be looking to see that you have work off to the side. Again, it's fine for you to rewrite it as doing this underneath. Just make sure you write limit each time. But if you don't want to write limit over and over, do it off to the side and label it as your work so I can see that and then come back and rewrite it. All right, so when we substitute that in, we get 1 over 4. Okay, questions with that? So let's take a look at your packet here. I want you to go ahead and do the first. Let's go 1 through 11. So your homework for tonight, do 1 through 11. I know we did a little bit of it, but 1 through 11. And if you're feeling brave, you can do the next few complications. I'll pick up with that next class. So again, next class, we'll continue with how to manipulate these algebraically. We'll take a look at special trait limits, absolute values, things like that. Have a wonderful day. TA Stinger 1.